Hi there, welcome in this new video in which we look at the exam of January 2025, and it's the exam of linear algebra. Well, this exam has the same format as in the previous years. For instance, in the first question we look at the basis and dimensions of all the four fundamental subspaces of a matrix. Then we have a look at an system of equation that is based on two values a and b, and you have to solve this system of equation and discuss based on the values of a and b. In question 3, what you have is really to fit a polynomial for values that are given for t minus 2, minus 1, 1 and 2, and this is really a least squares problem that you have to solve using the QR decomposition. And then finally you're given a matrix and you have to compute the factorizations. A is equal to R transpose R, one based on the pivots and one on the eigenvalues, and then you have to use the LU decomposition to solve a system of equations. Ax is equal to b for a b that is given. Well, let us start with the first question. So you have to find the basis and dimensions of all four fundamental subspaces of the matrix that is given. You have to compute the rank of the matrix A, and then express all the columns that are not in the column space as a function of the columns in the column space. And then finally you have to characterize all b's for which Ax is equal to b as a solution. Well, to solve this first question, we augment the matrix A with an identity matrix. We see that we have a pivot over here, and what we'll do is first create zeros below the pivots to bring the matrix into a echelon form, right? So we perform also these operations on the identity matrix because it will help us to find the left null space. So here we create zeros below the pivots by these two elementary row operations. If you perform these, this is what you obtain. Well, you have to go to the third column to find the pivot. We create 0 below the pivot using this elementary row operation, and since we want a pivot of 1, we multiply the second line by a third. If you do these calculations, this is what you obtain, and now you have an echelon form for the matrix A. We go to the row reduced echelon form by creating zeros above the pivot. So we have one more row operation to perform. Here it is, to create a 0 over here. If you do this operation, this is what you obtain. Since we have a line of zeros here, we see here that the rank is, well, the number of rows minus the number of lines that are 0. We see that the rank of A is 2. See also that there only are 2 pivots, so there are only 2 independent columns. Another way to see that the rank is 2. Well, the column space, which is a subspace of R3, can be found by taking, well, linear combinations of the original columns in the original matrix. This is what is written over here, right? And, well, the left null space you can obtain by considering this vector over here, right? If you left multiply the matrix A using this one over here, you'll produce this line of zeros, right? So the left null space is really a linear combination of this vector over here, and of course the left null space is also a subspace of R3. So you see that the dimension of the column space is 2, the dimension of the left null space is 1, 2 plus 1 is 3, it's okay. We can also check that this is correct by taking, well, the scalar product of the elements in the column space with the elements in the left null space. If you take the scalar product of this one times this one, you have 5 minus 4 minus 1, so this is 0. You can do this check with this one, scalar product with this one, and you will see that this is correct as well. You can easily see that the columns that are not in the column space, so this is the second one and the third one, well, you can read it over here and over here. So the second column is 3 times the first column. This is kind of obvious, you can see it over here. And the fourth column is minus 1 times the first column plus 1 time the third column, and this is also something that you can check. Well, now we have to go and have a look at the row space and the null space. These are subspaces of R4, right? We have 2 independent rows, so we have done row operations, so we can, well, take linear combinations of the original rows in the matrix A. This is what is done over here, but you can also work with the rows in the row reduced echelon form of A, and this will produce the same subspace. For the null space, what we have to do is, well, remember that the matrix is kind of divided in a identity matrix F and a 0, and the null space, well, it's obtained by considering this matrix minus F and then putting an identity matrix below. So this form we can obtain again by switching the second and the third column, right? So then you can easily obtain this matrix N here, minus F, so you have minus 3 plus 1, 0, minus 1, and then you put an identity matrix below. But then you have to take into account that you have to switch columns, so you have to switch rows, right? And if you do that, you obtain the null space. So it's a linear combinations of these vectors over here after you have done this switching, and this is what you obtain. Remember that this is a subspace of R4, dimension 2. This one is a subspace of R4, dimension 2. The sum of the dimensions is 4, which is correct. And you can check your results by taking the scalar product of this one with this one and this one. They should be perpendicular, and you can do the same scalar product of this one with this one and this one, and should be 0 as well. Of course, you can do the check with these two vectors as well. So remains the last part here of the question. Characterize the B's such that AX is equal to B as a solution. Well, for AX is equal to B to have a solution, well, B must be in the column space. So this means that you can write B as a linear combination of the columns of A. And this concludes this, well, first exercise of the exam. Well, in this second part of the exam, well, you have to solve a system of equations that is given, and you have to discuss, find the values of lowercase a and b for which this system of equations has no solutions, an infinite number of solutions, and a unique solution. For those values of a and b where you have an infinite number of solutions, you have to express this solution in full detail. So what we'll do is write the augmented system. Here we have the matrix A, and here you see the independent term here with the b's, right? So we'll start with this one as a pivot, and we'll create zeros below the pivot. The idea is to bring the system to an echelon form so that we can start discussing, right? Well, if we do these two elementary row operations, this is what you obtain. We can take this one as a pivot. Remember that normally a pivot cannot be 0, so we'll have to treat this case separately. And we can create a 0 below by this elementary row operation. So we kind of obtained this system here where we have two identical rows. So here this elementary row operation will create a line of zeros, and this is the system that is indeed in echelon form and that we can use to discuss. You can immediately see that if a is equal to 2, well, we have something 0 times variables is something that is not 0, so there are no solutions. If we take a is equal to -1 and we plug in, we see that the system that we obtain is this one over here. We'll have -3 here is equal to 3. What we can do is, well, divide by -3. This becomes a 1 and this becomes a -1. And then you can immediately see that if b is equal to 1, then you have an infinite number of solutions. If a is equal to -1 and b is different from 1, then you have no solutions, right? In all other cases, well, you have a unique solution because you have 3 equations here and 3 degrees of freedom, so you have a unique solution. So as the question asks, we have to look at this case where we have an infinite number of solutions. So this is the case a is equal to -1 and b is equal to 1, right? And then express the solution in full detail. So in this case, this is what we obtain. What we have to do, of course, here is create a line of zeros here. We have to create a 0 above the pivot over here, right? And then we have to multiply the line by -1 so that we create a 1 over here. If you do this, this is what you obtain, right? And now we know what to do if the system is in this form here. Again, identity matrix F and 0, 0. You can obtain this form by switching these two columns over here, right? So the particular solution is obtained by what is called in the course dp and adding a 0 below, but then you have to take into account that we have switched columns, so you have to switch rows. So this is the particular solution. Again, we can do this trick with the n. The f is simply this one here, minus f is 3, 0. We have to put an identity matrix, in this case of dimension 1, it's a scalar. Again, we have switched columns here, so we have to switch rows, right? So our solution for this case where we have an infinite number of solutions, it's the particular solution plus a combination of the vector that comes from the n matrix. So this is our solution explained in full detail. For this case, we have an infinite number of solutions. So this is concluding exercise 2 of the exam. Well, let us have a look at question 3, where you have to fit a second order polynomial given estimates at t is equal to -2, -1, 1, and 2. You'll have to solve the problem many times. You have to write it under a suitable form so that you can solve it, right? And since you have to solve it many times, probably that solving it using the QR decomposition will be a good idea. Once you have written the solution under the most suitable form, right, well, you have to solve it for given estimates of p at these times that were given above. So if you're preparing your exam, well, you should pause now and try to do this by yourself. Well, let us have a look at the solution of this problem. So what I've done here is written the first equation that you obtain by taking t is equal to -2. So I've replaced t by -2. On the right side you obtain this, and you have to set it equal to your estimate in -2. So this is the first equation, and you can find it over here. C0 minus 2 C1 plus 4 C2 is equal to the estimate in minus 2. And what I've done here in t is equal to minus 2, you can do for the other times as well. T is equal to minus 1, 1, and 2. And if you do this, you obtain the system that is written in a matrix format. We have 4 equations, 3 unknowns. We have a least squares problem. Since we have to solve this for different estimates over here and that the matrix remains the same, it makes sense to use the QR decomposition to solve this least squares problem. We can keep the first column. What we need for the first column of Q is of course a vector of length 1, so we have to divide by the length, which is, well, this one squared plus this one squared plus this one squared plus this one squared. It's 4 square root, and we divide by 2. So to obtain A2 bar, what we need to do, we need to subtract from A2 the projection of A2 on A1, right? This is what is done over here. But you can see here, you can clearly see it over here, that these two first vectors are orthogonal. Okay, so this one will be 0 and A2 bar will simply be A2. So again, we have to divide by the length. And here the length is square root of 10. Similarly, we can do something to obtain A3 bar. So we have to remove from A3 the projection of A3 on A2 bar and the projection of A3 on A1 bar. If you do this, you'll see that this term will not contribute. It's visible over here because the second and the third column are orthogonal. This one will contribute. If you compute this scalar product, you'll have 10, and this one is 4, right? It's the length squared. We had computed this before. If you compute this, well, you obtain this quantity for A3 bar. So again, we have to give it a length of 1, and this is how it's obtained. It's quite easy here. You can take a vector that is equivalent, so 1 minus 1 minus 1, 1, and this one is very easy to normalize. So now we have our matrix Q. Here it is, right? We have to decompose A as a Q matrix that is orthogonal and an R matrix that is upper triangular, right? So A is Q times R. So R is, if you multiply on both sides by Q transpose, R is Q transpose A. So here you have Q transpose, here you have A, and if you do the computations, and you should do the computation to make sure that you didn't do any mistakes, because these ones should come out 0. If you have made a mistake, they won't come out as zeros, right? So here is your R matrix, right? We need to solve AX is equal to B. So A is QR. We multiply on both sides by Q transpose, and we have here a system of equations. Rx is equal to Q transpose B. This will be interesting because this will remain the same all the time, and you have an upper triangular matrix, so you'll be able to do back substitution, right? So we need to see what is this Q transpose B. Here it is. This is Q transpose times B. It's the vector that contains the estimates, and if you compute this, this is what you obtain. We have the division by 2 here, the division by square root of 10, and there should be also a division by 2 over here. But we can get rid of those by simply multiplying this line by 2, this line by square root of 10, and this line by 2 as well. And this is what you obtain. This is now very easy. If you have new estimates, you only have to compute this independent term over here, and you'll have a system of equation that is in a good form to do back substitution. So if we take these values over here and you plug them in, right, in here, what you obtain is this system of equations over here. Here it's very easy to see that C2 is 0, C1 is 1, and since C2 is 0, well, C0 has to be 0 as well. Just as a matter of precaution, what I've done is kind of drawn the situation that we have here. So here in 1 we have an estimate in -1, in 2 we have an estimate in 3, in -1 we have an estimate in 1, and in -2 we have an estimate of -3. And what I've drawn here is this polynomial with C0 is equal to 0, C2 is equal to 0 as well, and C1 is equal to 1. So it's simply the polynomial t, right? And you look, and this sounds quite okay. So this is the solution of the third exercise. Let us have a look at the fourth question of the exam. You're given a matrix A, and you have to compute two R transpose R factorizations, one related to the pivots and one related to the eigenvalues. For the first factorization, you'll have to perform an LU decomposition. So here you're asked to solve a question AX is equal to B. The A matrix is of course the same, and you're given a B, right? Using the LU decomposition, and you have to explain why you would proceed like this. Well, let us first start with the R transpose R factorization of A. That's the one related with the eigenvalue. So we have to consider the following determinant, and we have to compute this determinant, right? It's quite difficult to compute, except if you try to create zeros in this determinant. You can do this by row operation or column operations, as you know that the determinant will be the same, right? So what you can do over here is replace column 1 by column 1 minus column 3, right? And this will create a 0 over here, but the additional advantage is that you'll have 3 minus lambda and lambda minus 3. So if you construct the determinant on this column over here, you can put it up front, right? So from this you already know that you will have an eigenvalue at 3. So the rest is just computing the determinant, right? And then putting the lambda minus 3 up front. Here's not the lambda minus 3, but the 3 minus lambda, and then you obtain a second order polynomial that you can factorize, and then you see that the eigenvalues are 3, 6, and 9. Once you have the eigenvalues, you have to compute the eigenvectors, and you have to use, well, eigenvectors of length 1. You have to normalize them because we're looking after a factorization of A, Q, lambda, Q transpose, where Q is orthogonal. So the thing that you have to do over here is solve this system of equation where you plug in over here the eigenvalue. Again, it's easier to create a few zeros to solve this system over here. Here, once you have done these row operations, well, you can kind of see here that V12 is 0, right? And that V11 and V13 have to take opposite values, right? So for instance, 1 and minus 1. So you have here 1, 0, minus 1. This is what we have computed over here. And then you have to give it a unit length. You can do something similar for the second eigenvalue and the third eigenvalue, right? Again, you try to obtain an equivalent system of equations, but with zeros in here, right? Once you have the 3 eigenvectors of unit length, you can stack them in a matrix Q, and this is the matrix Q we are looking after. So we have q lambda q transpose. In lambda, this is this diagonal matrix over here where you have the eigenvalues on the diagonal, and this matrix over here is actually the square root of lambda. You can write it like this because, of course, since the matrix over here is positive definite, the eigenvalues are positive, right? So you can write q lambda q transpose as r transpose r, and you see here that to have this decomposition, well, you have to write r as the square root of this lambda here times q transpose. So this is the, well, first r transpose r factorization, the one linked to the eigenvalues. Well, let us have a look now at the second factorization, the one that is linked to the pivot. So what we have to do on this matrix A is create an upper triangular matrix over here, and you can do this by creating zeros below the pivots. So here is our first pivot, and we have to create zeros below. We can do this using the following elementary row operations. If you perform these operations, this is what you obtain. Here we have the next pivot. We have to create a zero below, and you can do this using this elementary operation. So this is our upper triangular matrix U, and on the diagonal you have the pivots, right? And A is L times U, and in L what you do is take an identity matrix, and you put the multipliers at the right spot. So if you check L times U, you should obtain A. And what you can do, since the matrix is symmetric and the eigenvalues and the positive and the pivots are positive, you have a positive definite matrix. You can also obtain this type of factorization, L dl transpose, right? Because the matrix is symmetric, right? And in this matrix D, what you will have is the pivots, right? And since the matrix is positive definite, what you can do is write a factorization R transpose R. In this matrix, the pivots are positive, so you can write R as square root of D. So this will be a diagonal matrix with on the diagonal the square root of the pivots times L transpose. And this is this second factorization of A, the one related to the pivots. Well, let us have a look at the last part. We're given a system AX is equal to B, and you're asked to solve it using the LU decomposition, and then at the end, well, you are asked to explain why you would proceed like this. Well, you will proceed like this if you have to solve this type of problem several times with the same A and different B's. In this case, it makes sense to compute the LU decomposition and to solve two systems of equations that are really well suited for forward substitution and backward substitution. This will in this case be the most efficient way to solve the system of equation. So here we have done the LU decomposition. We have to solve AX is equal to B, so LU X is equal to B. So what you can do is define a variable Y and solve Ly is equal to B. L here is lower triangular. You can use forward substitution, and then once you have the Y, you say Ux is equal to Y, and you have forward substitution because here you have an R matrix here that is upper triangular, right? So if you solve this problem and you go through the calculations, it's quite easy because here you see y1 is 8, and here y2 is simply 10 minus 1/5 y1, right? And if you go through the calculations, you pretty easily obtain y1, y2, y3. Then you have to solve this system of equation where again you can use substitution, backward substitution in this case, because you start with x3. If you do the computations, you can see that x3 is equal to 1, x2 is equal to 1, and x1 is equal to 1. This concludes question 4, and this concludes the exam of this year. Thank you.